way. All right, so of course, as usual, let me get my laser pointer here. Always when we start about talking about semiconductor, people would recall something called Moore's law. And Moore's law has been really established several decades back. And Moore's law is a very simple statement, and it was saying that every 2 years, the number of transistors that are being integrated on a certain chip is going to be doubled every 2 years. And surprisingly, this has been predicted like, I don't know, probably 40, 50 years ago. And it has been sustained. It seems that the industry wanted to sustain this Moore's law. And this curves, as you can see, shows here the different years. So starting 1970 till 2020. And this is the number of transistors that has been integrated in a microprocessor. So starting like in the early 70s, maybe things was in the few thousands of transistor within a microprocessor. Today you can see, and you are reading it right, it's 50 billion transistors within the most advanced processors that are produced today. And if you do the math, you would see that really the order of magnitude that has been predicted, which is doubling the number of transistors every couple of years, has been preserved. So this is really amazing and really challenging in the same time. Other way to look at what's been happening in the semiconductor in terms of evolution is really what level of application has been driving all of the advances in this semiconductor industry. At the very beginning, in the early, I don't know, 50s, 60s, people were only producing like discrete devices. There was the first invention of the integrated circuit. And then we moved to the era of the mini computer. It's not yet the PC or the laptop that people are using today, but integrated circuit or circuitry was integrated in what we call the mini computer or the mainframes. And then we moved in the early 80s and the 90s till 2000. It was the PC and the internet was the main driver of all of the evolution that happened in all of these semiconductor and the electronics circuitry domain. Then following that came up the mobile phones. Of course, now you can imagine the mobile phone is in itself, the mobile phone is itself like a mini computer that you can put in your pocket, and it has numerous integration of lots of function, lots of circuitry within a small device. And then I would say in the late 2015, 2016 came the big data era and high performance computing, artificial intelligence, and 5G, which has to do of transferring all of these big data between different endpoints. And you have all of the portable devices, you have all of the integrated circuits within, I would say, the electronic circuitry that goes into the car and so on. So this is really has been tremendously driving what's happening in the semiconductor, has been tremendously driving more and more integration of electronic circuits within a smaller area. You can imagine today, if you look at the right of the screen here, everybody knows about the iPhone. This is kind of give you an understanding what has been happening in terms of evolution. Again, it satisfies Moore's law. If you go back in 2013, there was inside your iPhone was the A7 processor. Now you have something called the A15 processor, which exists in the iPhone 13 Pro Max. And if you look at the row in red here, the number of transistor was slightly around 1 billion transistor in 2013. Today, we have 15 billion transistors that are coexistent within the A15 processor within your iPhone. Of course, this has been tremendously growing. This has been advancing very, very fast. And I want to drive your your eyes to this technology perception. And I'm going to describe later in my slide what does mean this technology. In A7, it was like what we call the 28 nanometer technology. Today is the era of the 5 nanometer technology. So it's basically what it want to say from 28 to 5, it's scaling down. We're scaling down the sizes of devices. And when scaling down those sizes of devices to satisfy Moore's law, we are able to integrate more and more devices within a certain area. And this enables us to have more integrated functionality within smaller and smaller devices and gadgets that we have in our hand today. Okay, so moving forward, just a reminder that the transistor is the basic unit used to construct those integrated circuits. And you can see, I'm not going to describe in more detail, it's not a physics lessons, but this is the look and feel of the transistor. The manufactured transistor, of course, is magnified, I don't know, 1 million times, but this is how it looks like. It has like a source, drain, gate. And of course, each designer has the ability to change the length and width of the transistor to produce a certain functionality. And then people interconnect those transistors together to produce a certain functionality. And this is something that is being controlled by voltage on the gate. Whenever you have a certain bias here, you can control and create a channel here, and then current passes from the drain to source. One key feature in the transistor is the length of transistor, and we typically refer to this length. It's kind of correlated on the thing that I call the technology node here. In 1999, for instance, we had the 180 nanometer technology, which in a sense means that the minimum length of the transistor that can be fabricated is 180 nanometer. You cannot go beyond that. With the years, you can see the evolutions that happened. And today we are, as I said, in the 5 nanometer in production, working on developing a 3 nanometer transistor and maybe going beyond that in 2 nanometer and so on. So everything is being scaled down. And since the unit, which is the transistor, is being scaled down, so your circuitry is being scaled down. I'm not going to go into more details here. This is just a reminder of how this transistor operates. The more voltage that you put on the gate, the more current drive happens. Of course, this is like an old type of technology which uses 5 volt. Now you have something in 1 volt or sub 1 volt, I would say, in terms of supply voltage that can enable your whole circuitry. This is just an example to show you that if you can interconnect transistors together, you can build different types of circuitry. One of them is like this 2-stage amplifier, which like magnifies the signal from input to output. Also, some evolution happened on the device level. So here on the left, you can see this is what we call the planar transistor. And this has been actually used for quite some time until we reach what we call the 16 nanometer era. And we have to move from the planar 2D transistor to what we call the 3D transistor, which is a FinFET. And now we're moving into something called gate all around. I'm not going to describe, I mean, I would say the details why this is better. The FinFET has been better than planar and gate all around and so on. But at least the main advantages or the main drivers towards doing this evolution on the transistor level is to be able to drive higher current, have low leakage, and be able to be higher speed and less power consumption, which are key to be able to drive or to put in place those chips with high speed and less power consumption with very little leakage from the transistor side of things. And this has been enabled and developed and delivered in the 16 nanometer technology. Okay, going back to some, like I would say, primitive description or primitive definitions, what do we really mean by VLSI? VLSI is really the art of creating those electrical components from very small transistors that are mass produced together. As I said before, we have now the ability to integrate hundreds of millions of transistors per millimeter square. As an example, the Apple A14 packs 134 million transistors per millimeter square. So this is the reality. This is in production. And VLSI really includes 2 parts. It has the ability, it has 2 parts, which is creating a fabrication process. So there needs to be a manufacturing house that has a fabrication process or produce a fabrication process that can create and connect very small transistor. And this is all of the development that happens in the fabs. And the other part is the ability to design those geometrical shape that will create connected transistor using the process such that together they implement the intended design. So we always have this, I would say, differentiation between something that happens in a fab and something that happens within the designer or the design house. Those two together constitute this VLSI ability, or the ability to integrate more and more circuitry together. And the process of creating this geometrical design is a kind of top-down. So you start by a high-level system description, an abstract idea, and then you move from the system to the module, to the gate level, to the circuit, and the device level or transistor level to get all of these components integrated together to be ready for fabrication. And we're going to use the term layout, which what the fabrication house understand in terms of description of your circuitry. And when you have your layout ready, it goes into the stage we call the tape out. So we're taping out your design to be manufactured into a real design integrated within a bigger system like the telephone or the TVs or the car. Okay, so what is really computer-aided design nowadays? So in order for you can imagine, in order for you to design these types of complex circuits that have these millions of devices, you need to have access to a lot of software packages, lots of software tools. And those software tools are used to do, on a high level of abstraction, those types of activity. First, you need a tool that capture your design. So capture your idea, typically either in a text or a graphical representation. The other part of your software package is a package that would do an analysis. So the tool helps the designer understand the results of your architecture or the design you put in place. You will hear something called functional verification, or maybe simulation, or maybe rule checking, or electrical checking. So these are different tools that help you doing the analysis to make sure that what you intend to design is really verified through different software packages. And then there is something we call synthesis, which are the tool that automatically create what we call the next level of refinement. And maybe I will describe in more details what we mean by synthesis. Like an example, main synthesis tool creates circuits from a logic design and layout from circuits. So you have a representation that could be some description and you want to move that into a gate level. Or you have a representation that is called a netlist or a schematic and you want to move it to a more descriptive, understandable, I would say, step or level that is understood by the manufacturing house, which is a layout. And I'm going to talk about that in more details in the upcoming slides. Also, one thing that also I wanted people to kind of get an understanding of is, in terms of semiconductor companies, we have, I would say, different type of companies. So we have what we call fabless companies. So those are companies that only focus on designing integrated circuit, but they don't have a manufacturing facility. Example of those companies, maybe you heard about those: Qualcomm, Cirrus Logic, Broadcom, MediaTek, Apple, of course, Facebook, Amazon. So you can imagine people who say, oh, Facebook, it's a social media company. Do they design circuitry? Yes, they do design circuitry. Amazon also designs some circuitry that would go into their data center. So you can see more and more company getting into this IC design, I would say, cycle. There is another bucket which we call integrated design manufacturing, and those are companies that have both a design facility and a manufacturing facility. Example of this is Intel, for instance. You've heard about Intel. They are the one designing the microprocessor, but in the meantime, they have a large manufacturing or large fabrication house where they can manufacture their microprocessor or their designs into their fabs. Samsung is another example, TI, Analog Devices, and so on. And there are some things that we call the pure fab or pure foundry. It's just a manufacturing house. People that are working on those manufacturing house, they don't do designs, they just take designs from fabless companies or even from some of the integrated design manufacturing, and they fabricate those into their manufacturing facility. An example of this, you will hear something called TSMC. It's a very big fab. that is responsible on manufacturing all of the, I would say 60% of the designs or the integrated circuit designs go into TSMC, which exists in Taiwan. UMC is another fab that exists in Taiwan. SMIC is another fab. Global Foundry is another fab that exists in the United States and of course has branches worldwide. The one thing that I want to draw your attention to is if you look at back in 2009, the number of manufacturing facilities that was producing integrated circuit in the 130 nanometer technology were numerous. You can see tens or maybe 15 or 20 manufacturing houses that were able to manufacture designs in this 130 nanometer. If you look today, you will see you only have 2 and maybe 3. Let's assume that Intel is still producing in the 7 and will continue investing in more advanced technology. We have only 3 fabs that are able to manufacturing IC design in these advanced type of technologies such as 7 nanometer. The 3 are TSMC, Samsung, and I would add to this one Intel as well. So if we want to look at the whole ecosystem, so in order for anyone to be able to manufacture IC designs, what are the different companies? What are the different, I would say, semiconductor players, semiconductor companies? You can see that we have companies that produce intellectual property, chips or cores, like ARM, like Rambus, Synopsys, Cadence. You can see that you need companies that give you access to what we call electronic design automation tool, which are all of the software packages that designers are using to integrate those designs. You need to have access to material subsystems. You need to have access to what we call wafer fab equipment. So a typical manufacturing facility like TSMC needs to get the latest, I would say, scanner machine or the latest machinery that would be able to print your circuitry on wafer. An example of such big companies is ASML. And you need, of course, the 3, I would say, companies that I described earlier, fabless companies, IDMs or foundries like TSMC, UMC, SMIC, and so on. And you can see here different logos, different example of the different players that plays into this overall semiconductor ecosystem. And in a nutshell, this semiconductor ecosystem produce chips that are integrated by other companies in bigger systems like Google, like Apple, like Facebook, like Tesla. You can see here who's manufacturing car, Amazon, Microsoft. All of these produce end-to-end products like the iPhone, like, I don't know, the car, the plane. So really this to give you an overview that circuitry today exists in our everyday gadgets that we use in everyday life. So it's a major, important strategic component in our day-to-day life today. Also, quickly to give you an overview about as I said, the top foundry, TSMC, as I said before, is producing or has a market share of 60% of the market. And you can imagine the amount of revenue that these companies produce is in the order of $56 or $57 billion. And these are the top 10 foundry. You can see they are mostly in Pacific Asia, like TSMC, Samsung in Korea, UMC, Global Foundry in the US. Other, I would say, company exists in China mainland. Very quickly, here are the top 10 semiconductor vendors by revenue. You can see Samsung is on the top. Intel comes next, SK Hynix, Micron, Qualcomm, Broadcom, MediaTek. So these are, like, I would say, the top 10 player by revenue. And the order of magnitude of revenue is in the order of $75 million. $75 billion, I'd say. ASML is also a key player in the, I would say, wafer equipment. And it's really very important company because today it's the only company that can produce the equipment that is used in the fab in the 7 and 5 nanometer, which we call the extreme ultraviolet type of technology. All right, now moving to the core of my presentation, I want to describe, okay, as I said before, what it would take for anyone to design an integrated circuit from a concept or from a system spec until the final, I would say, chip assembly. You can see several different steps. You start by system spec, you go through an architectural level, and then transistor level or gate level, full custom layout, or what we call place and route, and then there is physical verification, and then parasitic and timing. So different steps described here also, same thing. You have a system specification until you go to the packaging and testing. And the integrated circuit design, it really involves the creation of these electronic components such as transistor, resistor, capacitor, and interconnect those devices together in order to put that in a piece of silicon and produce a certain functionality. And I said the number of integration or the level of integration, we're talking about billions of devices integrated together in a small millimeter square type of shape. Okay, and there is something that happens also in the fab. So even after you do what we call the chip assembly, you deliver that to the fab, and there are some other, I would say, advanced type of software packages like the resolution enhancement technique that has been introduced, maybe starting from the 90 nanometer, and this is something that the fab take care of to do some post-processing. And if we have time, we're going to touch base. Why do we need to do that? This is something that the designer don't do or doesn't account for, but it is accounted in the fab in order to produce or do the final tape out. Okay, so if we look at the system spec, what is system spec? This is what we call the concept stage. So let's imagine that you have a big system like this one. Let's say this is like a transceiver, which is a transmitter and receiver, which exists in any telephone or any mobile phone. You want first to kind of put the concept, have a specification of the overall product. And typically what the designer uses at this stage is very simple models, very simple mathematical models to describe each of these components that exist in that system. And typically they use MATLAB, Simulink, and the purpose really is to have these big system level description and being able to verify that in a very simple way, very fast way. So you don't adding any level of complexity to the blocks have the drawback of slowing down your simulation time. So this is what we call the concept or system level design. Now, moving down the road, you want to have something slightly more accurate to describe your system. And this is where you start partitioning your system into blocks. And we have two main, I would say, differentiation in terms of blocks. We have either blocks are being partitioned as being analog blocks, or they are being partitioned as digital blocks. And on the left-hand side here of this flow, this is the analog flow for people who are designing analog circuits. On the right side of things is a simplified way of designing digital blocks. Okay, and of course you need to have this, I would say, framework or backbone, which you can use to kind of do a mixed signal level simulation. So what is the impact of analog blocks within the digital flow and vice versa? So we have these framework to be able to do this mixed level signal verification. And analog blocks on an architectural level are represented by what we call analog and mixed signal languages. An example of that is VHDL AMS or Verilog AMS. From the digital block, of course, several of you maybe heard about the VHDL and Verilog description. So this is a second level of representation. Instead of using Simulink and MATLAB, we go a little deeper in terms of modeling our system in a slightly more accurate way. And this is what we call behavioral modeling. So it's a means of mathematically describing physical phenomena. It adds a certain level of details. And of course, the benefit of using these behavioral modeling techniques is to have a very fast simulation to describe your system. Speed up could be 10x or 1000x versus the very accurate level of the transistor or the logical set or gate level. VHDL AMS, as I said, is an extension of the VHDL standard that has been delivered in 1993, and it enables to extend the VHDL to supply analog and mixed signal designer with a certain high-level language to describe their system. If we look here, this is an example of, let's say, we have an op-amp, an operational amplifier. It can be modeled using this extension of VHDL AMS. This is a very simplistic like modeling of an op-amp. It just says that the output, or this is just an amplifier. So we have the output is a magnifier of the input. Of course, you can add lots of more level of details if you want to describe more, I would say, characteristics of the op-amp. You can do that through the description in the architecture itself. Moving forward in the analog side of things, of course, you finalized your AMS on a system level. You want to have your block level with a more accurate description, really the most accurate description of your physical design that is going to be manufacturing. And this is where the transistor level or SPICE modeling come into place. This is the most accurate way to verify your analog design. For large design, simulation could consume days of CPU time. SPICE is really a general purpose simulator that simulate your design. And you have access to what we call device models. And maybe you heard about BSIM3, BSIM4, EKV model. These are really very famous device modeling, device models that accurately describe how the device or how the transistor behave in real life. So this step you have in terms of software packages that are supplied by EDA vendor. We have what we call the SPICE simulator. It takes as an input the netlist, it takes device model, and it takes the input, output, and the analysis type, and would show you simulation results. So let's say you have this operational amplifier. You start using a schematic capture or a netlist to describe the interconnectivity between those different transistors that constitute your design. And then you throw that into a SPICE simulator, and you can see the different characteristics that you want out of this amplifier. It could be like the gain of the amplifier. You want to check the slew rate. You want to check different functionality that you wish to be achieved by this architecture. Some very well-known commercial tools available in the market are ELDO from Siemens, or AFS is another tool also supplied from Siemens, HSpice by Synopsys, or Spectre by Cadence. This is example of commercial tool for SPICE level simulator. You can see here, this is a two-stage amplifier. This is a schematic, and this is the netlist. This is the SPICE syntax. I'm not going to go into detail, but it's a really well-known standard to describe your connectivity between the different transistors. You can describe the length, width of the transistor, the number of fingers, and so on. And once you write this netlist, you can throw that into a simulator, and it would simulate your design. So this is, I would say, the most accurate way of verifying your design from an analog perspective. Now, if we move to the digital side of things, equally from an architectural level, you have a way to describe your circuitry in terms of VHDL or Verilog on what we call the register transfer logic. And you can see here, this is a very simple description of like a D flip-flop, and this is the VHDL code from a behavioral perspective that describe this flip-flop. Tools that uses or consume VHDL or Verilog for functional verification or for digital functional verification. Example of those tools, you can see something like ModelSem, Questa by Siemens EDA, VCS by Synopsys, Excellium by Cadence. The next step after you describe behavior or digital circuitry is the step that we call the gate level, or we need to synthesize this type of description into a gate level description, because the gate is the actual description of your design. And by gate, I mean and, or, any logic gate, NOR, and so on. So this step of moving from an architectural level to a gate level, we call it a logic synthesis level, or we use logic synthesis tools. Where the behavioral description is turned into a design implementation, an actual gate implementation. So the flip-flop that you saw in the previous slide is going to be transformed from a behavioral description to a gate level. You can see here an inverter, an AND gate that is interconnected together. And we have tools that automatically reads these behavioral description and move those into a gate level description. Tools that do these logic synthesis for the ASIC side of things are An example of those tools, you will hear something called Design Compiler by Synopsys, Encounter by Cadence, and Catapult by Siemens EDA. All right, now moving forward, we finished, I would say, from an IC design perspective, we started by a system level. We moved into an architectural description. Then we moved to the most accurate way to functionally verify your design, which is for the analog is a transistor spice level simulator. For the digital side, it is gate level simulation. Now we want to move to the, I would say, the back end representation. All of the previous, we call it by our terminology, front end description. Now we want to move to the back end, which is the description that is understood by the manufacturing facility. And the key word here is layout. Okay, so actually in the actual world, the transistor that is being manufactured looks like this in a 3D fashion. If we do a cross section, it would be, I would say, in a very simplistic way, it's a set of polygons that are interconnected together. Here you have the poly or the gate. Here in blue, you have your metal. In green, you have your diffusion. So the next step that the designers need to account for, he needs to take his previous representation, whether it's a netlist or a schematic capture or a digital set of gates that are interconnected in a VHDL fashion, and he needs to transform that into another representation, which is the layout representation. And why do we need to do that? Because this is the standard that is being understood by the fab or the manufacturing facilities that would manufacture your design at the end of the day. So this is an example. As you can see, this is a very simplistic way of looking at layout. This is an inverter. This is how it looks like on a transistor level, PMOS interconnected to an NMOS. And then this is the layout representation. Okay, you will tell me, how are we going to move from this representation to this representation? Through a software package that we call a layout editor or a full custom layout editor, or in the digital world, it is called place and route tools. Okay, so this is just a look at how these is represented in the layout transformation world, I would say. Now, if we look at the analog side of things, as I said, it is called full custom layout, or the tools that are being supplied by the major, I would say, EDA vendors is a full custom layout. Example of those is Pixis by Siemens. Maybe you heard about Virtuoso by Cadence or Custom Compiler by Synopsys. And the full custom layouts is really a polygon level layout using simple polygon pusher software. It is driven by a schematic or a netlist. So as I said, we reach that phase where we have a schematic or netlist, and then we want to transform that into a layout. So the input to the tool is schematic or netlist, and the output is a standard format or standard layout format, and a very famous standard that are known across the industry or people who are doing integrated circuit design is GDS or OASIS or LEFDEF. So as you see here, we start by a schematic. The tool has different components that would help you transform this schematic or a netlist to a GDS or OASIS. If we dig deeper into these layout tools from the analog perspective, it has several components within it. A layout editor, which really in a simplistic way, you can look at it as something similar to your paintbrush, for instance. It's an editor where you can draw different polygons and connect them together. It has inside of it what we call a device generator, which is something that would help you automate the generation of your layout. So here, it's really a facility inside the tool that build automatic primitive devices. For instance, here, you can have within your layout something that would automatically reduce an inductance for you. Or this is a multi-finger transistor. All you have to do is just a push of a button and you say, I need a transistor with this dimension, width and length and number of fingers, and it will automatically create your layout for you. It can generate different devices, transistor, resistor, capacitor, inductors, guard rings, and so on.
Dr. Sherif, sorry to interrupt you, but we still have 10 minutes.
Okay, great, thank you. Okay, I'm gonna try to move slightly faster. The other components in a layout editor from an analog perspective is what we call an SDL flow, or schematic driven layout. And really this is something that resides on top of a device generator, and it creates a layout out of a logic database. It uses a process file device generator to create the layout. So you can imagine that you have this schematic on the left side of things, and you want to generate your equivalent layout. So it will call your device generator under the hood, generate the different devices. You can see here, those are mostly transistor, here are capacitors, and in yellow here, these are the interconnects. Of course, this is a semi-automated way, and custom or analog or full custom layout is an analog art. So this is just a tool that would help you to create your primitive devices, and then you have to compact these designs together in order to have a very compacted interconnected design. Okay, moving to the digital side of things are slightly easier. And the main component or the basic building block, such as when we said analog, we said the basic building block is a transistor. Here, for the digital side of things, the main building block is a standard cell. And by standard cell, I mean an AND, an OR, or an XOR, a flip-flop, or a latch. And the layout of a standard cell, by definition, has a fixed length and a variable width. So this is an example of an inverter as a digital cell, and this is the equivalent standard cell. This is a buffer, and this is the equivalent standard cell. The beauty about these standard cell is that they have fixed heights. So once they are, I would say, abutted together or placed very close to each other, you will see that their power supply and their ground are automatically interconnected together. And this is the core. This is the core of the place and route tools that really is in very automated way of kind of supplying or producing your final layout. Of course, here we're talking about place and route tools, and this is in the digital era. The placement is the step that assigned exact location of cells within a chip core area, and it takes a synthesized circuit along with a technology library, place all of these standard cells close to each other. As you can see here in green, those are standard cells that are placed abutted together. And the placer really needs to be very intelligent to minimize the total wire length, optimize the timing and power. So this is an example of
هو دكتور شريف ممكن يكون عنده connection issues وهيرجع تاني إن شاء الله.
I don't know, somehow I got disconnected. Let me quickly share my screen. Okay, I should be back now.
Yes, you are.
Yes, it's back.
Okay, sorry about that. Okay, so I was talking about the routing, which is a step of creating all the wires to connect the different placed cells together. You can see here that the router should make sure that the design, of course, meet the required timing, metal density. One key metric is called PPA, which is power performance area. So really wants to minimize the power, improve the performance, and minimize the area. Legacy speaking, there was something called channel routing, and now today we are using what we call area routing, which produces more dense designs and we can use wiring that goes over the different cells that are interconnected together. You can see this is an example of integrated circuit chip that has lots of wiring and lots of cell interconnected together. Okay, now maybe the last step in the design that the designer need to take care of is making sure that he satisfies the design rules that are supplied by the foundry. So the layout is really measured by a set of geometrical constraints. So there are rules that are imposed by the foundry. So you cannot place, for instance, a metal wire in proximity to another metal wires very close to each other. There is a certain rule that says there is a minimum spacing between those metal wires. There is a minimum width for a certain layout. There is a minimum overlap of a certain layer on another layer. There is a minimum enclosure, for instance, on a certain via. So these are all design rule specific that are tied to a specific process node. So if we're talking about, for instance, the 28 nanometer or the 7 nanometer, they have their own set of design rules. And of course, when we say minimum width, minimum spacing, minimum overlap, this is a very simplistic way of looking at design rules. But nevertheless, this is just to give you a sense that when you interconnect your devices together to put together a layout, you need to be careful to satisfy the rules that are supplied by the foundry. Otherwise, if you go and fabricate your design in the foundry, it will not function if you violate your rules. And in order to do that, you need to have, I would say, a tool that verify your design. And this is where physical verification come into play. I'm going to skip. This was just an illustration of the complexity of the rules. So it's not just a single spacing rule per metal wire. This is like a spacing rule for M1. There are 7 different rules that now required us to kind of come up with what we call the equation-based nanometer DRC. But I'm going to, for the sake of time, skip that one. So if we look at the DRC flow is really a system that provides the common language. So you need to describe the different constraints that come from the fab in terms of rules. And this is put that together in what we call a DRC deck. You have your layout tool. So you are going to generate your GDS file as we described earlier. So maybe a place and route, maybe through a full custom layout editor. And then you would input that to what we call a DRC engine. And the DRC engine would scan your layout. It has a scan line that goes through your layout and make sure that you are satisfying all of the rules that are supplied by the foundry. And if there is a violation, it will show you those violations, and it's a responsibility of the designer to fix those design rules. Example of tools here, commercial tool, you have Caliber by Siemens, PVS by Cadence, and ICV by Synopsys. The other important aspect in terms of physical verification is what we call layout versus schematic, or LVS. And LVS is a process that determines whether an IC layout corresponds to the initial schematic or circuit. So you recall that we moved from a certain representation to another representation, and we need to make sure that the layout representation is conforming to the schematic representation. And this is where LVS come into play. Because if you miss a connection or do a short circuit, that would damage the whole functionality of the circuit. And this is where LVS need to ensure that the layout device parameters or the circuit is wired and interconnected properly. And as you can imagine, the input of an LVS tool is a layout, is what we call an LVS deck, and is your source netlist. And it makes sure that the layout and the source netlist are equivalent together. Again, same set of tools, Caliber, ICV, PVS. The last step, maybe from a design side that I'm going to cover today, is the interconnect parasitics. And you can imagine that when you put together circuit in a SPICE level netlist or in a gate level netlist, you kind of consider that the wiring is ideal. So if you have an interconnect that connects a device to the other, really the reality is metal wires are non-ideal. They have what we call parasitic something that you don't want to occur. So each wire here has a resistance, a wire closer to a wire has a certain capacitance. So you have something that even though you don't want it to happen, it will happen anyway. So you will have some resistance, some capacitance that you didn't intend in your original design, but they do exist in your final design or your final layout. So why do we need parasitic extraction? The goal is performing parasitic extraction is to model resistance, capacitance, inductance, simulate your whole design. So you need to take that into account, simulate your whole design with the existence of those parasitics and make sure that you meet your spec. If you do not meet your spec, then you need to modify your layout such that you meet your spec. And an example of commercial tools that are used for parasitic extraction is Calibre XRC, Exact 3D. Those are supplied by Siemens, Star RCXT by Synopsys, and Quantance or QRC by Cadence. I think I'm kind of running out of time. Maybe just cover this slide. It's that the growth and complexity of the design rule are, as well as scaling to advanced node, has generated really additional tools, checks from the design side of things. I tried to cover the most fundamental, I would say, part of the flow until physical verification with the three main components like DRC, LVS, and extraction. But reality is in today's era, we have lots and lots of other tools. For instance, the number of rules and their complexity are becoming very complex. And now you cannot use just simple DRC to code your rule, but you need maybe a pattern matching engine. Yield is becoming an issue, and the simple DRC pass-fail is not enough. And here comes the notion of what we call design for manufacturability. I don't know, can I use like a couple of more minutes to go, or how am I doing in timing?
Okay, we still have like 5 minutes. Yes, you can do it.
Okay, I'm gonna try to wrap up in the next 5 minutes. I'm gonna skip that slide. This is just to give you an overview of the complexity and the number of in the physical verification side of things, which is our main focus of my group. How we grew in terms of the number of tools is not just DRC and LVS and PEX. You see numerous tools, but I'm not going to cover those. It's just to give you an insight about the number of packages and tools in advanced node technologies that are needed. And here comes the notion of what we call design for manufacturability. And really the design for manufacturability is, it's not really anymore a pass and fail criteria like we used to have in DRC, but it's the notion of having a higher yield. And there are numerous tools that would be used by the designer actually to be able to make sure that your design is yielding high. I'm not going to cover this. This is going to take time, but this was a lot of things to cover here today. This is just to give you now that from an IC design and IC fab, there are lots and lots of tools. It's not just DRC, LVS extraction. There is pattern matching. There is something we call PERC. There is design for manufacturability. There is litho-friendly design, which take really some of the variations that happens into the fab and can be accounted by designer to make sure that their designs are robust enough. Maybe the last part of my presentation would focus on something we call the resolution enhancement technique. And if we just give a very quick glance of what happens in the fab, when you go and manufacture your design, so you have, as we described, your layout, you provide your layout to the fab. And what happens really in order to print out your layout on a wafer is you have a source of light, and the source of light goes through a mask, and then it prints onto a wafer. And really, if we skip very quickly here, I just want to bring you the idea here. When we scale down our, I would say, devices, the wire lengths and the widths are very, very small. And this causes what we call diffraction of light, because really when you go into the fab and you manufacture things, the light would drop into your mask and it would cause something called diffraction. So you will see that your design would be not what you wished to be printed on your wafer. And this is something that existed, but is very, very highly manifested in very advanced technology. So you can imagine if this is your target in a 350 nanometer, there is no problem. Now, because we are using a wavelength of 193 nanometer and we're printing things into 45 or 25 or maybe now 5 nanometer, you will see that if you do nothing about your design, this is how your your design will print. It will be completely, I would say, disconnected because of this diffraction effects. And I'm going to skip that. This is where a tool that we call optical proximity correction comes into play. And the idea is very, very basic. Basically, what needs to, and this happens into the fab, actually, it doesn't happen in the design house. What really the fab does is that it changes the layouts that the designer would give to the fab, such that it compensates of those diffraction effects. And with OPC, you can see that your layout will print correctly.
Thank you so much, Dr. Sherif.
Okay.
That's an amazing presentation. Now we have questions from the audience. There is a question. What are the required qualifications for digital back-end track?
Okay, so maybe I wanted to share very quickly a final slide that I had to give. Maybe it's an opportunity to show you what I call job opportunities at Siemens. As I described, what we are producing here from Siemens EDA, we are a software company. So we are producing software products. And we have very exciting opportunity to develop the leading edge, what we call innovative software products. And just for your reference, I know several of the audience are undergrad or people who just graduated. These are the link for the opening and jobs and job descriptions that we have. From our perspective, we are looking for good software developer, knowledgeable in C and C++, familiar with software algorithms and data structure, having some background in semiconductor is an asset, knowledge of Unix, Linux, and good communication skills. So really just to make sure that people understand our domain or the EDA domain, we are producing software packages. So people need to understand what are the electronic application levels that our customers are using, and they need to focus on developing all of our software packages. So this is on a high level what is required for somebody to join an EDA company. Going back to your question, Salma, you were talking about somebody who is doing digital design. Was that the question?
Yes, digital backend.
Okay, so from a digital back end, I mean, this is the part when I say when you say back end, it's probably people who are focusing on migrating the front end designs, which is the step that I described in my presentation, moving from a net list or a front-end representation like a digital circuitry to a layout. So typically the qualification of that person, he needs to be understanding very well the electronic side of things. He needs to understand what it means, circuit, layout, and he needs to understand all of the aspect of the integrated circuit flow, integrated circuit designs. He needs to have background on the device levels, and he needs to be able to use CAD tools like layout and place and route tools to be able to design your digital circuitry in the back end side of things. I hope that answered your question.
Yes, thank you so much, Dr. Sherif. We were honored to have you today. So our next speaker is Dr. Nermeen, Engineer Nermeen. Yeah. So Engineer Nermeen is a principal product manager in the design to silicon division at Siemens in Egypt. She is supporting Caliber DRC products and managing Caliber Auto Waivers activities. She has been working in Siemens and previously Mentor Graphics for more than 21 years. Before joining Caliber, Engineer Nermeen worked on different teams in Mentor Graphics such as CBS, customer support, and design kits. She received her bachelor degree in electronics and communication from Ain Shams University, and then she earned her MBA from Edinburgh Business School. We're honored to have you, Engineer Nermeen, with us today, and you can start your own presentation.
Thank you. Let me share my slides. Okay. Let me know when you see my presentation.
Yeah.
Okay.
We can't see it now.
Okay. So let me start. Today I'm going to present how to accelerate early design exploration and verification. Yes?
We can't see the slides.
You cannot?
Yeah.
Okay, let me make sure that I shared the slides correctly. Okay, yeah, I'm sorry. Okay, let me know as soon as you see my slides.
Yes, we can see the screen now.
Not yet?
No, we can see it.
You can now?
Yeah, yes, we can.
Okay, let me start again.
Yep.
Today I'm going to present how to accelerate early design exploration and verification, and what are the different tools and features that Siemens DI software supports to improve the runtime and cut down manual debugging effort for early design and physical verification. Let's start by defining the system on chip. System on chip is an IC which integrates all the components into a single chip. It may contain analog, digital, mixed signal, and other radio frequency functions, all lying on a single chip substrate. It may include a CPU, memory, USB controller, power management circuits, and others. As Dr. Sherif mentioned, today IPs and system on chips are on every small gadget that we are currently using. Especially system on chips are very common in electronics industry due to its low power consumption. The system on chip designer goes through the different stages of the place and route flow to assemble his chip by integrating the different blocks that represent the different functions from the different block owners. With advanced nodes, the competition of being the first to the market, designers don't have the luxury of waiting till the chip blocks are completely finished to start their chip assembly. And accordingly, system on chip designer aim to start chip integration in parallel with block development, as it is clear in the figure on the middle. The different blocks are at different stages of development. None of the blocks is complete as the system on chip designer started his initial floor planning phase. And they get completed as the system on chip designer moves on through his design flow. At each stage of the design flow, the designer is running different physical verification iterations to capture the DRC violation and work on fixing them. The goal at each stage is to minimize the number of iterations and definitely reduce the runtime of each iteration, in addition to focusing only on the violations that are relevant to this stage, in parallel with reducing the manual work and improving the debugging process. Parallel implementation of block and chip level design and running physical verification, mainly DRC, on incomplete dirty blocks has lots of challenges. Usually, at the very early phase of floor planning, the number of reported violations in the unfinished blocks is huge. And it is not a trivial task to differentiate between the block level violation and the top routing violation. In addition, lots of systematic issues may be widely distributed or across design, leading to an enormous number of errors. This huge number of violations may lead to long DRC runtime, gigantic DRC result database file that is not easy to open using results viewer tools to review the violation, all of which will make debugging and fixing violations really very difficult. The system on chip designer would like to push the block's violations to the block owner to fix them and focus on fixing the routing violation as well as the violation that may be generated because of some systematic issues. And his main goal is to capture and fix this routing violation early enough in the design cycle to reduce the time to market and avoid last-minute surprises. These are typical examples of the systematic issues that may be widely distributed across the design, leading to a massive number of errors. Off-grid block placements at the system on chip level, merged IP outside of the system on chip macro footprint, routing in IP on reserved routing layer, incorrect VIA type on clock nets. All of these issues may lead to huge number of violations. Easily capturing these violations and fixing them will significantly reduce the number of reported DRC violations. So the aim here is to help the system-on-chip designer capture these issues early in the design cycle and help them or help him with fixing such kind of issues. To be able to help the system-on-chip designer achieve his goals, Siemens introduced its new Caliber Recon solution. This is a complete package of several features that will help designer work around the current challenges and accelerate early design exploration and verification while different components are still immature. As Dr. Sherif mentioned in his presentation, any DRC run has two main components that are affecting the runtime: the foundry deck and the input design. If the foundry deck contains lots of checks, it will definitely take longer time to run. Same for input design. As it gets bigger, it will take longer time to run. Accordingly, to have faster DRC runs, we need to run smaller version of the rule decks. That means unselecting some of the checks that are not relevant to this early stage and still ensure good coverage. And from layout perspective, we need to exclude or gray box the unfinished blocks that are still very dirty and only keep the interface region of the system on chip for the system on chip designer to be able to capture the interface violation. This will help to reduce the number of reported violations and accordingly reduce the runtime. This is exactly what Recon does, and we will see together how Recon is doing this in an automatic way and the positive impact of this in both runtime and memory consumption. Recon also supports the generation of some color maps on the output results through DRC Analyzer tool that will help the designer find and fix the systematic issues from early floor planning stage through the final tape out. These features are also integrated with other Caliber tools to allow better debugging and quick fixes as it uses the Foundry deck without any modification. Therefore, Caliber Recon is very effective in identifying, integrating issues, providing fast feedback to the design team for proper corrective actions, resulting in much better turnaround time and faster time to market. This is our chip verification recommended flow. Remember that our main objective is to minimize the number of iterations of each stage of chip development and reduce the runtime per iteration. At early stages, where the system on chip designer has started to assemble his chip and lots of blocks are still at early phases, are still under development, the user is not in need to run full deck. At this stage, he should be interested only on the basic checks. Accordingly, he needs to run in the Recon mode and use gray box to exclude unfinished blocks. He may also use the DRC Analyze for results analysis and systematic issues capturing and fixing. Moving on to the stage where the blocks are more mature, but he still has lots of violations, so it is still recommended to use Recon to focus on checks that are convenient for this stage. And use traditional auto waiver to waive the false violation from the finished blocks. And keep on iterating here up till the DRC run become almost clean. The user can then switch to inverse Recon, where he will be able to run the section or the set of checks that were unselected in the Recon mode on the blocks that are still or in this stage where he needs to keep on running here up till he have better results from DRC to move to the final sign-off stage where he need to run the full deck on the complete design and still use auto waiver to waive the agreed on false violations. Let's go through the different features of the Recon solution in more details, and let's start by Recon check selection. Some rule checks are known to be prone to longer runtime in the presence of error. Deselecting such rules can significantly speed the runs. But how does the designer decide which set of checks to deselect? Deselecting the checks with many operations, or deselecting the connectivity checks, or maybe the antenna checks? Which group of checks does the designer needs to unselect to have better runtime? Selecting the best set of checks to run in a reasonable time with good coverage is not easy, and it may require a lot of advanced analysis as well as some editing to the foundry deck. The main objective of Caliber Recon check selection tool is that it automatically deselects runtime intensive checks that are not significant for early development phases. And the good thing about it is that it does not require any modification to the foundry rule deck. And the user just needs to enable this by a new switch in the Caliber invocation run, which is pretty easy. Recon is mainly excluding the rules that are likely to experience long runtime and unlikely to provide actionable results to address systematic issues, like connectivity checks or multi-patterning checks or pattern matching checks. Actually, those set of checks are not important at all at these early phases. We still have blocks that are not finished yet. How come we are checking connectivity, or how come we are checking multi-patterning checks and this kind of a check, that they may have a problem at any or at some location that have like multiple violations being reported on other location on the chip. So these checks at this early phase will cause like lots of violations to be reported without any real value, and the user will not be able to fix this violation at this early phase. So it's better to exclude or to completely unselect this set of checks at this phase of run. And the main advantage here is that the Recon overcomes all the challenges of chip verification, where it's significant by deselecting this set of checks, it significantly improves the runtime and memory consumption, in addition to generating much smaller results database where the user will be able to open and review using the layout viewer tools or the results viewer tools. As agreed, Recon helps to improve runtime and memory consumption. As you can see from the left figure below, the blue bars represent, let me also try to get my, as you can see from the graph here, the blue bars represent the runtime of the DRC run, and the orange bar represent the runtime of the Recon run. As you can see, we have significant improvement in performance with the Recon run that can reach up to 14x improvement in runtime. And what about memory consumption? Recon also improved the memory consumption. Again, the blue bars represent the DRC run, and the orange bar represent the Recon run memory consumption analysis. And again, we were able to achieve an 18x improvement in memory consumption. Also, Caliber Recon, as agreed, deselect some of the checks. On average, the Caliber Recon tool reduced the number of checks performed by about 50% across the different processes. And it also reduced the number of reported violations. We may reach up to 70% from the original DRC violation that used to be reported in the original DRC run. And these graphs show how the number or the actual number of DRC checks that used to run on the original DRC run, and how the number of DRC executed checks is reduced when running with Recon, that is being represented by the orange bars. And on the other graph here on the right, it represents the number of violations that may reach, as agreed, up to 70% of the original DRC violations. But these 70% are more meaningful violations that may have even better impact or better value at this very early stage. Caliber recon verification not only helps system on chip designer with early chip level verification, but also support early block verification. Because block and chip designer are being done in parallel, a block designer can run caliber recon verification on the block. If errors are reported, then the block designer can fix the systematic issues. But if the recon results are clean, the block can be passed to the chip, while the block designer runs the remaining rules in parallel with the block. As shown in the figure below, running the caliber recon tools on blocks or on the different tiles may result in an improvement up to 8x in runtime and 4x memory improvement. As you can see here, these are the columns that represent the DRC run for both the runtime and memory consumptions, and those are the one representing the recon run. For these three different blocks or tiles, we were able to reduce the runtime from 0.45 hours down to 0.1 hours, from 1.3 hours down to 0.15 hours, and from 40.6 hours down to 1.56 hours. So it is a significant improvement, a real significant improvement in performance. Same for memory consumption. And what about the full chip? At the beginning, we were not even able at all to have it running using the full DRC deck in the complete design. But when we use recon with this set of selected checks, we were able to have it completed in 10.5 hours, which is a great achievement within a reasonable memory consumption. So recon check selection really helped to improve the runtime and memory consumptions of the full chip by selecting the set of checks that are relevant to this stage of the chip assembly. What about the gray box? Gray box is where we exclude some portions of the design, mainly excluding the unfinished blocks, also to improve the runtime and reduce the number of reported violations. Gray box helps the user to exclude dirty or unfinished blocks. It removes the data from the specific cells without removing geometries from higher up parents. Accordingly, any routing violations over the specified cell will still be captured. In addition, user can keep certain halo around the removed geometries by sizing the extent of the cell down to help to capture the interface violation between the specified cell and their neighbor. Excluding some polygons from the core of the blocks may lead to some introduced false violations. Accordingly, we are recommending running gray box in parallel with auto waiver, where we can waive the false violation that may be introduced by excluding some of the polygons from the chip. This is an example of the chip. We have here 3 blocks. Let's assume that we are going to select this block A that is still under development. This is the representation of block A. We are going to exclude this core of the block, and we are going to have a waiver layer or a marker layer around the excluded area to waive any false violation that may be introduced by excluding this core of the block. And this is the region on the interface where it is still be considered in the DRC run for the system on chip designer to capture the interface violation between this block A and block B, which is important for him to capture at this stage and work on fixing them. So the main advantage of gray box is that it isolates unfinished block from the run to speed runtime, as well as reducing the number of reported violations to enhance debugging and having the system on chip designer mainly focus on the integration violation as we described for block A. It is clear from the snapshot on the left how the number of reported violations got significantly decreased when some of the unfinished blocks got excluded. those are the ones that were excluded, and we have no violations reported here. We may only have some violations reported on the interface of these excluded blocks, but we still have lots of violations being reported on the blocks that were not excluded. And here on the bar chart, it is clear how recon helps to improve the runtime. The blue bars represent the original DRC run, and when we run with recon gray box, the runtime has significantly reduced as represented by these green bars. And if we run both recon check selection in parallel with gray box, we will be even able to get better performance that is represented by these light blue bars. In case of channel routing, where we have routing layer passing over the blocks, the user may be interested to capture the routing violation over the blocks or between the routing layers and some specified block layers. Recon gray box gives the user the option of preserving some of the block layers from being excluded, and accordingly will be considered in the DRC run. So in case of any violation in this routing layer or between this routing layer and the preserved layer on the block, they will still be captured. So in this example, this is the extent of the cell, this is the extent of the excluded region, and this is the waiver layer or the marker layer where we waive the violation. But since we have metal 1 in this example as a preserved layer, we should still be able to capture metal 1 spacing violation on the routing layer, and also metal 1 spacing violation between the routing layer over the block and metal 1 layer inside the block. Those layers are not going to be ignored or waived, but they are going to be reported back as real violation to the user. Interface-only flow is one of the very helpful flow in case the user would like to waive the violation from some specified blocks and only capture the violation reported on the interface region of these specified blocks. The tool will automatically create a marker layer on the blocks that the users are not interested to capture the violations from, to waive these violations so they will not be reported back to the user, and only the violations on the interfaces are going to be reported to the user. In general, interface flow is not helping on improving the runtime of the chip assembly or the chip physical verification for the chip, because we are not excluding any polygons or any regions from the design. But it will help with debugging because we will have the violations only reported on the areas where the system on chip designer would like to have the violations being reported on. So we will have less number of violations being reported, and definitely this will help with the debugging process. The include cell flow. The include cell flow is mainly target the block owners. It's not the same as the flows that we discussed about earlier, where they were mainly targeting the system on chip design. But from block owner perspective, he may be also interested to validate his block within the context of the full chip. But the point here is that he does not want to run the full chip because this will consume lots of time and we will have lots of violations being reported. He would like to capture only the violations reported on his block, maybe with a halo around it or an interface area around his block. So if we assume that this is the block that the block owner is interested to capture the violations from, and this is the area where he would like to consider as an interface to his block, we will this include cell flow will only consider this area in the DRC run, and will exclude all the other polygons from the rest of the chip. And again, excluding any polygons from the design may introduce some false violation. And that's why we also have here some marker layer that is being automatically added to waive the violation that may be generated in this area. But here we will give the block owner the flexibility of capturing only the violation at his block and the area around it. And as we agreed, focusing only on the block with the area around it will definitely reduce the number of reported violations and will definitely improve the runtime compared to running on the full chip. These are some snapshots for the results generated from the 3 different gray box flows. In the first one, for gray box, where we excluded some cells with some preserved layers, violations are only reported on the interface of the excluded blocks, and some violations are being reported over the excluded areas for the preserved layers. And again, lots of violations are still reported on the blocks that are not excluded. For include cell flow, we have the violations only reported on the block for the block owner, or on the block that the block owner is focusing on, maybe with an interface area around this block. And with the interface only flow, we have all the violations only reported on the interface region for the system on chip designer to focus only on the interface region and fix these violations, fix these integration violations, because as agreed earlier, the block owner violation should be pushed to the block owners to fix them. So the system on chip only cares about these interface violations, and those are the ones he should work on to fix. Let's go through the last recon feature, which is the DRC analyze, the recon DRC analyzer. Caliber Recon DRC analyzer helps the designer quickly analyze their design and visually looks at their distribution and at the distribution of the error to identify the opportunistic areas to quickly to fix the violation and enhance the layout quality. The DRC analyzer can help the designer to draw different histograms for chip analysis. These histograms can be based on the cells that are available on the design, or we may even grid the design into different windows and draw these kind of histograms based on these windows. The DRC analyzer can also help to draw some color maps on the results that is being generated from the DRC runs. And again, these color maps may be drawn based on cells or based on windows. The main advantage here of this DRC analyzer is that these kind of color maps help the user understand where are the areas in the design that have most of the violations being reported. It may highlight a certain systematic issues for the user to go on and fix it. And the good thing about it is that it runs using the Foundry rule deck as it is without any modification to the Foundry deck. It also gives the user some flexibility to specify categories, window size, ranges of the different histograms, and all these kind of stuff. The DRC analyzer, as agreed in the previous slide, can help the user identify and capture the systematic issues to quickly capture them and work on fixing them. And these are two cases where the design analyzer helped to capture off-grid placements of one of the blocks where we have most of the violations being reported in this red window of the color map. And accordingly, it points out to the system on chip designer that we have a block that has been placed off-grid. And in other example, it helped here to show that we have a problem with the fill, where we have all the violation or most of violations being reported in the red window, where we have a problem with the fill, and this has been pointed to the system on chip designer to go and fix this fill issue with the blocks that is being placed at this location. Here comes an end, or by this slide, we finish all what is related to chip assembly physical verification. But since the 3D IC market is growing, and we have lots of packaging techniques that have been recently introduced, it is a good, let me see this opportunity also to discuss some packaging techniques and the differences between 2.5D and 3D stacking, and the 3D stack tools that Siemens DI software supports for 3D IC validation. IC packaging. Let's go through some packaging techniques and start by single die package. Traditionally, in 1970s, the package include one single die in the package, usually one function. There were several advantages to this scenario, such that the fact that different chip companies could concentrate on creating devices that fell into their expertise. Also, each chip die could be implemented at the most appropriate technology node. The high-performance digital logic chip could be created at the latest and greatest and most expensive technology node, for example, while the lower performance digital logic devices could be created using an earlier and most or more affordable technology, what we call it legacy nodes. Of course, there are some disadvantages to this approach as well, such as the fact that resulting circuit boards will be large, heavy, consume more power. Furthermore, there would be significant hit in performance because it takes relatively long time in the scheme of things for signal to propagate across the board from one chip package to another. However, when more functionality is required for smaller spaces, a new type of chip came out, which is the system on chip, which is still a single die, but within this single die, they manage to fit different functions. They can have analog circuit, digital circuit, optical circuit. It can have most of the component of the computer, like processor, memory, IOs, DSPs, and other. System on a chip is what we talked about earlier in the presentation. So we have already talked about it a lot. But the advantage of a system on chip is that you get the highest performance with the lowest power consumption and the shorter communication, as the design is very compact and fit all in one die. And communication between different systems is very short. Great, lots of advantages for system on a chip. But does this mean that we do not have any disadvantages? Definitely not. We still have some disadvantages. The disadvantages is that the design is so complex. It is resource intensive and time consuming. Also, adding the analog or RF functions on the same die at the digital logic means that the analog RF functions are not as optimal as they could be if implemented using a dedicated process node for their implementation. Also, you can run into all sorts of noise isolation problems and all these kind of stuff. It is also not easy to change the design in the future to enhance the existing functionality or add any new features because it's a complex design. It requires lots of validations and the design cycle is not easy, as we explained earlier. A multi-chip module comes next. It is the first step toward 2.5D technology. It is generally an electronic assembly, such as a package with a number of conductor terminals or pins, where multiple integrated circuits, ICs or chip, and semiconductor dies and other discrete components are integrated horizontally, usually onto a unifying substrate. So it works as a single device. The advantage of using the multi-chip module package is that it is much simpler than system on chip. It allows the manufacturer to use multiple components for modularity and to improve yield over conventional ICs. The multi-chip module started like this and then evolved in the system in package. For these multi-chip modules and for system on package, when we have multiple dies here, they don't have to be using the same technology. We can have different dies. Each die could be implemented or on a different technology, which is great and provides lots of flexibility in this space. Let's now focus more on the system on package. System in a package components are comprised of multiple integrated circuits together in a same package where they are connected internally. Components like DRAM, flash memories, processors, and other basic electronic components are often contained in a system in package, making them fairly capable and contained system. System in package can be stacked vertically or horizontally with either wire bond or solder bumps connection. It also evolved to real 2.D pumps or 3D technologies, where a silicon interposer is placed between the system and chip substrate and the dies, where this silicon interposer has what we call it through silicon vase, connecting the metallization layer on its upper and lower substrate to be able to connect between the different dies and the substrate. This approach has several advantages over a system on chip, including the fact that one can include analog, digital, and radio frequency dies in the same package, where each die is implemented using that domain most appropriate technology node, as we agreed earlier. It has the highest density of transistor. It is a simple design with optimized cost, with optimized size, and better performance. They may contain active and passive devices as resistor and capacitors. Furthermore, when it comes to updating the design, it's pretty easy because in case you would like to enhance the existing functionality or would like to add a new feature, you still need to do something, but it is not a complete design rework. You will just need to rework some of the existing dies that are available in this package. This is an example of 2.5D and the 3D advanced package. As you can see here, we have the package substrate. Then we do have an interposer with these TSVs or through silicon vase to connect between the dies and the substrate. In the 2.5D, we have the dies being assembled in a horizontal manner, but in 3D IC, we can have the dies stacked over each other. Let's have a closer look on this. This is the 2D, where we have the interposer. We have different dies like a controller. We have the memory chip, and we have also the interposer. And this is how the front end looks like. This is the substrate. This is the interposer with the TSV to connect between the different dies on top of the interposer and the substrate. And we have here the macro bumps or micro bumps to connect the interposer to the substrate. On the 3D stack side or 3D IC assembly, as agreed, we may have like different dies stacked over each other. So here we have multiple memory blocks, we have multiple controller chips, and also we have the interposer. And this is how the front end looks like. We still have the substrate, we still have the interposer, but in this 3D stack assembly, we have the dies assembled over each other and not the same as the 2.5D where they are assembled side by side. Advanced packaging techniques like 2.5D and 3D offers offers the ultimate flexibility in product design, and brings packages technologies to front for innovation and are critical to products' performance, functions, and cost. From time to market perspective, customer can reuse technology blocks that do not change frequently or do not scale to develop chiplets, which allow for faster innovation and shorten time to market. From a performance and efficiency perspective, it allows the integration of high-density interconnected chips into a packaged module, delivering improved bandwidth, latency, and power efficiency. And from cost perspective, customer can reuse blocks such as analog IOs, RF, and those that do not change frequently or scale well. So they can still be developed using legacy nodes as agreed, and only update or use the advanced technology to implement the logic blocks that scale well and needs these advanced technology nodes for their implementation. Siemens DI software supports Calibre 3D stack that enables assembly level verification and packaging, assembly level verification of packaging interfaces. As discussed earlier, traditional ICs are self-contained and verified at the chip level using Calibre DRC products like DRC, LVS, and PEX, as Dr. Sherif highlighted in his slides. But what about these new packaging techniques that have like lots of packages assembled together? How do we verify them? How can we make sure that they are aligned correctly, or the connectivity is still maintained between the different die that are assembled together? The 3D stack tool that Siemens supports provide a fast and an accurate way to do an assembly level verification of the die-to-die or die-to-interposer interfaces. It operates on the interface geometries between chip design from multiple process nodes, including die bumps, C4 bumps, and ball grid arrays, to perform the DRC alignment verification and LVS connectivity checking of the complete multi-die 2.5 and 3 DIC system. It also generates the required files for exact 3D to perform multi-die PEX if required. Let's have a closer look to the 3D stack tools that Siemens support. To validate physical alignment, 3D stack accounts for offset values along the X and Y axes and the rotation and magnification factors specified for the different dies placement. Because when we place these dies over each other, we may have some offset in the X and Y direction. We may have some dies that have like some rotation, like 90-degree rotation, 100-degree rotation, and something like this. Some dies may be even scaled up or scaled down. So the dies may have like different precisions. All of these kind of stuff, Calibre 3D stacks account for them and is able to consider while validating the physical alignment. And in that case, it mainly checks for the alignment between the pads from the different dies to make sure that they are aligned together, or the center of these pads from one package to another are well aligned. It also captures any extra die or any missing dies from any of the stacked dies that form the 3D IC assembly. What about LVS? For connectivity checking, shorts, opens, text label mismatches are detected. The tool checks for connectivity between connected shapes when there is a source netlist present. And when there is no source netlist present, it will check for matching text strings on connected shapes. So in that example, or here in this example, we have like multiple dies. In each of these dies pads, we have like text labels. To check connectivity, we need to make sure that the text labels, for instance, on these pads on die 2 are the same as those text labels in die 4, on the pads of die 4. And if they are matching, that means that we have correct connectivity between them. This is if we do not have a source netlist. But if we have a source netlist, we make sure that these text labels are matching and also match these pin names in the source netlist. And in case we have a full source netlist, we can manage this interposer or package either as a black box, just to check the connectivity between them and the dies over them, or as a white box where we also check the connectivity inside this package or interposer. And what about extraction? In some cases, it is also required to extract the die-to-die coupling capacitance. Calibre 3D Stack built the interface for Calibre PEX tools, mainly exact for Siemens. It generates the different required files that the interface, like the interface annotated GDS or interface MIPT files, and all these files of all these kind of files required for parasitic extraction or required for exact tools to be able to extract the interface or coupling capacitance between the different dies and make sure that it is within the acceptable values. So Calibre 3D Stack helped to do the different kind of physical verification required for this 2.5D and 3D stack, which is kind of new technology, booming or more commonly used these days by big foundries like TSMC because of this flexibility that they provide, as we discussed earlier. And I believe this is the end of my presentation, and I will be willing I will be happy to answer any question you may have on my presentation or the different topics that we have covered.
Thank you so much, Engineer Nermeen. It was an honor to have you today with us. And we haven't received any questions. Yes, we haven't. Thank you all for attending today, and see you soon, inshallah, in our next day.
I mean,
Thank you.
Thank you,
all for
Dr. Yahya.
yeah, thank you, Nermeen. Great talk. And we look forward to seeing you more in the future, inshallah. And thank you, Salma. Thank you, Dr. Sherif. Very, very nice organization. Thank you very much.
Thank you.
Thank you, Dr. Yahya, and thanks for all the people that joined the talk today. Thank you, Salma, for organizing this.
Welcome.
Yeah.
Okay.
Bye-bye. Have a great night.
Goodbye.
Bye.